Let's now go ahead and show how transformers work practically. Here we have this, we run this again. We have the usual path. The number of examples we shall use is 250. We have this. Notice that we've selected a sequence length of just 5 right here. Get that. And that's fine. So we've prepared our data set already. Also note that we have this input which gets into the decoder, or rather the encoder, and we have this shifted input which gets into the decoder, just like with the first model we worked with. And then we have the output right here. Then getting into modeling, we have the self-attention model, which we shall explain straight away. For the self-attention model, basically what we're doing is implementing what we had in the slides. We have the score or energy right here, which we get by the multiplication of the query and the transpose of the key. So here we specify transpose B is true. So we have QR times K transpose here, which gives us our score. Another way of finding this matrix multiplication of the query and the key transpose is by working with the AND sum operation, which comes with TensorFlow. The way we could look at this is that the AND sum operator actually helps us focus just on the shapes of the tensors. Now here, this AND sum operator takes some sort of string. So here we have this string right here, and then we have the inputs. Now this query input takes in this, so it's the query input is actually matched to this ijk. Now this ijk represents the shape of the query. So if the query has a shape, say 20, or the query tensor has a shape, say 20 by 30 by say 56, then I, J and K can be matched to this, but they're not actually the same thing. So we have that. Then the key here is matched with this IBC. Then the output is what we have here. Now the way that we define the output is in such a way that if we were to follow the rules of matrix multiplication, then there must be a matching. So what does that mean? It means that if we want to multiply the query and the key, obviously if we have this ijk and then we have IBC, if we want to multiply the query and the key, we take off the batch dimension. So if we take off this batch dimension, multiplying this two should give us normally JC. Obviously K and B must be the same for us to be able to multiply this two. So multiplying this two will give us JC, and that's simply from the rules of matrix multiplication. Now if we were to multiply the query and the transpose of the key, then we are not multiplying JK and BC, but instead CB. So obviously from here we should have JB. So that's what we should get. So what does that mean? It means if we include this I, we could do this, include I, that's a batch dimension, and then this is what we get. So the AND sum operator, once given this, can automatically compute the query times the key transpose just based on the fact that it's able to see the kind of way we align our inputs to obtain the outputs. So that said, this means to obtain the query times key transpose, we could simply use this tool. So right here we could replace this with this. So it's fine to use this. This is the batch dimension, the I, see the I's are maintained, and then we're just playing around with the JK and BC, noting that this JK or this JKBC turns to JB because this BC is turned to CB, and then JKCB turns to JB, and obviously that gives us the query times the key transpose. Once we have that, the next step is for us to divide all through by the square root of the key dimension. So here we have the model size, which represents the key size, and then we just do this casting to ensure that it's actually a float value. So after this, we have now the square root, obviously, because we have the score, which is equals the score value now becomes is same value divided by the square root of the key. So this is basically what we're implementing right here. Then now the next steps will involve two kinds of or two possible kinds of masking. That's the pattern masking and then the causal masking. We've seen already the causal masking, but the pattern masking hasn't yet been treated. To better understand this pattern masking, we shall just show an output we get from doing the pattern masking. So let's have this, let's run this. Supposing we have this kind of input, so we have this 1 1 and then 0 0 0 1 8 2 0 0 0 9 0 0 0. Then after going through a pattern masking, we should obtain another tensor where all the values which had position 0 should have either 1 or 0, and then the other values with a position which is not actually equal 0 should have a 1 or a 0 different from the 1 or 0 where we had the zeros. So in this case, for example, wherever we don't have a 0, we see we turn it to a 0. Here, wherever we have a 0, we turn it to a 1. See here, for example, 182 turns to 0 0 0, 0 0 turns to 1 1, 9 turns to 0, and then the rest turns to 1. Now, the aim of this pattern masking is because many times in our data sets, we may have to pad so that we match up with a sequence length. So supposing we have an input like je, for example, let's say I love deep learning, for example, and that we have a sequence length of say 5. In this case, if I, for example, has occupies say the 4th place or the 5th place in the vocabulary, and then love occupies say the 6th place, and then deep learning occupies say the 24th place, then we'll have to pad this with zeros right up to the end to match up with a sequence length of, for example, 10. So as you see, this the kind of value or the kind of tensor we shall be inputting. But the problem we may come across here is that this inputs where we have the patterns or where we have the zeros will now cause us to have attention weights which will be affected by the zeros, of which the zeros actually have no role to play when training our model, since they don't actually contain any information or any useful information in our translation model. So in that sense, what we want to do is to make sure we're able to differentiate this parts where we have this patterns from these other sections where we actually have the sentences or the words which we are trying to translate. Now with that, we'll see how this function actually works. The most important part of this function is the tf.mat.equal right here. So let's take this off and then look at a simple example. Suppose we have this, and then right here we have 2 3 say 6, then 0 0. Run this. See how we obtain this Boolean tensor where we have false wherever we have a value different from 0, and then we have true whenever the value is equal to 0. So basically we're just comparing each item of this with 0. And in this case, we have false, 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 true, true. Now, the next thing we could do is we could cast this. If we cast this to be a float, so we could cast this as d type equals tf.float 32, for example. Run this again. You see, now all this have been converted into ones and then this into zeros. So this tensor starts to come out clearly. Now, once we have this, the job is actually already done, but all we need to do right here is just to modify the shape. That's by adding this extra dimension, and then with this by selecting or taking off a first dimension, such that we are having this exact kind of shape, so that we are able to fit this with our score. Now, talking about the score, we've seen from here already that we're able to find this pattern mask using the pattern mask right here. But the way this is added onto the mask is such that we first of all take the mask, we multiply by -1, that is multiply by a very small negative number, a very large negative number like this number, for example. So multiplying this by a very large negative number will permit us have, for example, in this case, if we have this, we say -1 times 10 to the power of 10. So we have this, for example, multiply this, and there we go. We see that we have this 0 0 0, and then these two very large negative numbers wherever we have zeros. And now what we notice again from this is that if we have TF the softmax, we take the softmax of this, we'll notice again that wherever we had the zeros actually gives us 0 values. That tells us that they do not matter much at the level of decision making, since the attention weights only care about the non-zero values, or the values which initially were non-zeros, like this values, this kind of values, and then just this value. So in the case, for example, where we have this, let's put in this, you see that all the rest zeros. If we add that, there we go. And it's with this same technique that right here we have our score, then this mask where we have this multiplied by this large negative number, such that when we have this, actually, because this is the score equals score plus this, so at every position where our score will be added with a very large negative number, that the softmax at that position is going to be a 0. And at every position where our score is going to be added with a 0, then the softmax is going to be maintained, or the softmax is going to be proportional to its value, not as compared to the other positions where we have this very large negative number, which will make the softmax to turn to 0. So these values, the softmax of these values will tend to 0, obviously, because these values, when multiplied with very large negative numbers, will become zeros after the softmax, as we've seen just right here. Then as for the other mask, which is the look ahead or casual mask, where we want all the future words in the sentence not to affect the past words, we are going to use this band part method from tf.linearc package. So let's take this again and then see how the look ahead mask is being generated. So supposing we have this, let's put it that way, then we run this. Let's just take off this and then have some ones right here. 1 1 1 1. Run that. We have this error. Take care of this dimension. Let's include that second dimension. That's fine. We'll print out the ahead mask now. Run that, and there we go. This is what we have. Now let's modify this. So supposing we have this new tensor now, running this, you see we obtain this. Now what do we notice here? We notice here that, for example, for supposing the first input only itself is important in whatever decision making that has to be carried out. Now if we have this first two inputs, only the second input and the previous input are actually important. If we have 3 inputs, only this third input, its previous input, and the input before this input actually are important. So what's important to note here is that when doing or when taking decisions, what matters is the past and not the future. So that's why it's called a look ahead mask, such that we actually avoid looking ahead. Now what goes on after this is we have now the product of what we just got here and the negative of a very large number, which gives us this new tensor. Notice again that with this tensor we have a 0 0 0 0 0 0, and then for all the values where we had ones, we now have this large negative number. And if we had to, let's say we take this to be AH, so we define this to be AH, and then if we had to do TF dot neural network softmax of AH, so let's print this out. You now see clearly the effect of the look ahead mask, where actually all these values turn to 0, as we could see clearly from here. Now note that we shall be using the look ahead mask only at the level of the decoder for just one of the multi-head self-attention layers, whereas for the pattern mask we shall use it for all the different, or we shall use it in all the different layers. Now that we understand exactly how these masks are created, we can now get back to the code. So right here we have the pattern mask, or the pattern mask, which we get from the pattern mask, and this pattern mask takes in the sequence. Now actually the sequence is basically the input sentence, which in the encoder will be the input, and in the decoder will be the shifted output. So that's what we have for this pattern mask. Then for the total mask, initially we're supposing our total mask is the pattern mask. Now if our look ahead masking is true, that is if we are at the level of the decoder for the first multi-layer attention block, then we shall have this causal or look ahead masking. In that case, we're going to have our total mask, which is this pattern mask, and we're going to add it up with the causal mask or the look ahead mask. Now the way it's going to work is that if we had the 0 0 1 1 1, as you could see from this, now adding it up with this other one will create a situation where not only we are taking off the parts where the input is made of the 0 patterns, but we are also making sure that at a given point in the sequence length, predictions actually depend on either the present or the past. So coming back to this, we have this total mask now, which is the ahead mask, or the total mask, which is the pattern mask, plus the ahead mask. And then we have our score, which is the same as the score, plus the total max times this large negative number. We've understood how important this operation is, because once we are able to multiply with this large negative number and then we add it up to the score, all the values which are zeros, or rather all the values which are ones for the total max, now will become very large negative numbers, and those large negative numbers plus the score values will turn the score values to very large negative numbers at those positions, and hence they wouldn't actually be taken into consideration with the softmax, since all the values will turn into 0. So with that, we have this. We could remodify our code to have this, so that's fine. Now we calculate our alignment score. For our alignment score, we have the softmax of our score basically, and then we have the head or context vector, which is computed using the matrix multiplication of the alignment score and the values which were inputted right here. Now note that the sequence is actually the input sentence. We have our look ahead masking, which at the base is considered to be false, so by default this is false, but whenever we want it to be true, we can simply specify, so that's fine. Now we could actually test this function right here. So let's have this. We have our query, we have our key, we have our value. This query is this 3520, key 3520, value 3520. We have this input sentences. Notice how we have in this byte size of 333, we have this input sentences right here, and then look how we have this patterns. That's what we get right here, and we're going to print this out so that we could see the pattern mask that is generated once we have this. And then we specify that the look ahead mask is true. So initially we are having we're supposing that we are having to work with causal masking. So let's run this now. Instead of having the shapes, we could take this off. Take this off right here. Run this, and that's fine. So now we see exactly what we actually want to obtain. For the pattern mask, we see that at all positions we have zeros, except wherever we have this 0 right here. All these positions zeros, and then except this one, see this 9, and then all the rest. And then for the causal masking, we see that upper right triangular matrix, which is all 1, same year and same year. Normally this mask right here should have dimension 355, but since we're going to be adding it up with a score or even with a causal mask at this point, because if we get into this, we're going to be adding it up with a causal mask that we calculated from here, or this ahead mask, then what happens is adding this 2 will be in such a way that this is going to replicate itself 5 times, and this will replicate itself 5 times, and this replicates itself 5 times, so that it matches up with the dimensions of this, and this respectively. So that said, once these 2 are added up, we're going to have a new mask, which now is going to be multiplied by this, added to the score, and then calculated where the softmax is going to be calculated. So from this, let's print out again now the total mask. We now look at the values we get from the total mask. So as we had said previously, this values now, we have this, all these values, the first, we see clearly how all the values give us 0, 0, 0, 0, and then only this point gives us a 1. Now here we have all 1s, so we could see clearly how we have all 1s, and then here we have 2 actually because of this 1 right here. So basically what we're doing is that we're adding up this 2. And we can see that effect very clearly in this last place here, where all these values were all 1s, whereas here all these values are 0s. We see how adding them up gives us this. So it tells us that practically for this last sentence, only the first word will matter because we just have 1 word. So that's it. So once we have this max, now we can now have our alignment, which could print out. I'll run this again. So that's fine. We see exactly what we get now as our attention weights. And now that the self-attention layer has been understood, we can now move on to the multi-head attention layer. We've taken out the prints. We can now clean this up, and then running this again, we see clearly how we have now this output with dimension batch size, by sequence length, by model size. Now after building the self-attention layer, we could go ahead with the multi-head attention layer. Now supposing that we have H self-attention layers which is stacked up to form the multi-head attention layer, then we shall have 8 of this kind of layers, where we start with the dense layers, and then we have the attention layer proper. Then after we have this, but with the difference that after the attention layers, we now concatenate them to form this kind of output. So we know that the kind of inputs we have in the attention layer is actually the D model. In this case, we've considered D model to be H, so we have the D model divided by the number of heads. In this case, it's NH. So don't confuse this H with a small h we shall be using the code. Now coming back to the code, this actually is the NH we're talking about. This NH right here, NH, NH, that's the number of heads we're working with. And here NH. Now let's take that off. So that's fine. Now we have the query size, the key size, and then the value size, which is the model size divided by H. We're trying to ensure that we're working only with integers right here. So that's why we have this, so that we have only whole numbers. Now we have defined self H as H, and then we have this WQ, WK, and then WV, which happen to be the dense layers we had defined here. So this is like WQ, WK, and then yeah, we have WV. Let's just modify this to dense Q, yeah, dense K, and then yeah, we have dense V. For this we have that. That's fine. So while we're getting into this, we have the dense Q. Now that's fine. So what we'll do here is we'll define this dense layer for each of the heads. So for each head we have that dense layer. Practically for each head we have this dense layer, for each head we have this dense layer. Now also notice that for this dense layer which comes after the concatenation, we just have 1. So that's logical, since after that we don't have to repeat this output over H dense layers again. Then from this, we now define our self-attention model, which is basically what we had from this right here. So we have the self-attention model. We specify the key size, and then in the call we have the key, the query, the key, the value, the sequence as usual for the padding masking, and then the look ahead masking to say whether we're going to use look ahead masking or not. Then from this, we now have that for I in range, that's for each and every head. We have the head, that's the value of the head we get, is basically the output of the self-attention. So it's just like doing exactly what we had here. We just basically calling self-attention right here. We specify all these values. Notice how we pick out a given I for this I. So we're picking out that, and then after that, we now, for every step, because we've defined these heads, for every step we're just gathering the heads, and then later on we concatenate these heads on the second axis, and then we pass this through this dense layer, or this dense output layer, which now gives us our final output, which we call heads. Also notice how this dense output actually has model size number of outputs. Let's now go ahead and test our multi-head attention layer. So right here we have this. We could run this now, and then we'll see exactly the kind of shape we have obtained at the end. Now we've had this query to have this, to take the shape, then our sequence, the shape, which is normal since our sequence is kind of like the input from our data set. And then this query has this batch size, sequence length, and then the model size. So what we do again is that we're going to print out the head shape right in here. So we run that again, and we get what we have here. So we see that this 128 is divided by 8. This 8 is actually the model size, or rather the number of heads. So this 8 is the number of heads, and then 128 is the model size. So right here we divide 128 by 8, so we get 16, and that's why each of the head gives this kind of output. Now after the concatenation, this is what we actually join all this, and then we pass it through this dense output, which ensures that we have this same kind of output actually. So yeah, we could print out again the heads, that shape, run that, and that's fine. So that's what we get. After constructing the multi-head attention layer, we can now move on to the encoder layer, or single encoder layer. With this encoder layer, we're just going to follow what was prescribed in the paper. We start with the multi-head attention. We then have this ResNet-like addition and then normalization. Then we pass it through the feed-forward layer. In this feed-forward block here, again, we have, after this feed-forward block, we have the input being added with the outputs to have this output we get here, then it's normalized. We now recreate this as an encoder layer where we have this multi-attention. Then the output of the multi-attention is added with a encoder input right here. So we have this input plus encoder output, which gives now the output. And then the input to the feed forward is actually the encoder output, or rather is the multi-attention output. Then inside the feed forward, we have this first dense layer, which is dense 1, which takes in this feed forward input, which is the output from the multi-attention layer. And we also note that this dense 1 has this output of model size times 4 neurons, while dense 2, that's this next dense layer, the dense layer which follows the first feed forward layer, has instead an output of model size neurons before we have the dropout. And the reason why we chose this to be like this is simply because right here in the paper, the authors had taken this D model to be, that's a model size to be 512, and then decided that this inner layer, which is this dense 1 right here, should have a dimensionality DFF of 2048. Now 2048 divided by 512 is 4, so we're just going to replicate this, and that's why we have this model size times 4 right here for our first feed forward layer. And once we're done with that, we do the same ResNet-like addition where we take in the input and then we add it with the output to get our new output. Then from this, we now have the layer normalization on the output. So this is in a nutshell our encoder layer. Now we could test this very simply. Here we define the vocabulary size, we define the model size, we define the value for h, that's the number of heads, and then we could run this and then run this. We're told we have this error right here. There's this normalization. Okay, so there's this encoder normalization that we kept out. So we'll run this again, and that's fine. Now the next step is our encoder itself, which is made of the different encoder layers we've just seen. So we have n different encoder layers which make up the whole encoder. Now in our encoder layer, we shall also include the positional encoding, such that once we get an input, we add that positional encoding, and then we have now the different encoder layers which come up. So here we have our positional encoding function, which takes in the model size, and then for all the different positions, we're going to repeat actually the steps. Now the different positions here stand for each and every time step we have. So for the first time step, the second, and right up to the last time step. And for each of these time steps, we have to get the values of the positional encoder, which is defined right here, for every I which is in the range model size. Now if I is even, that is if this modulo 2 is equal to 0, now for an even number like say 6 modulo 2, you see that gives us 0. But if this were an odd number, that would give us a 1. So if I is even, what we do is we simply apply the formula which we had described already. So we have this, the sign of the position divided by 10,000. So we could add this right here and then have that. So we have this 10,000 to the power of I divided by model size. And again, here we have this. And now when I is odd, we have I minus 1. Recall that in the paper it was given us 2i, and 2i plus 1, 2i. So it means if we have an odd number, we have to remove 1 from that, and obviously that will give us an even number. So here we have the positional encoding of I when working with even numbers, and that when working with odd numbers. So when we're done with a given time step, as we can see right here, once we're done with this given time step, the next thing to do is to attach this to our output list, which is what is done right here. Now before doing this, we add a dimension such that, for example, with this, given that with this we just have this one dimension, so we add an additional dimension like this, such that after this we can now concatenate that to have an output which is of dimension sequence length, and the model size. We take that off and then test our positional embedding function, and with this the kind of shape we have. Now for each of this, we could also print out the value of PE. Now let's take this back. Okay, so we're doing this for each position, so let's run that again. Take the shape, and that's fine. So this is what we get. Now after passing through this expand dimension, what we get is now a shape 128 right up to the end, such that when concatenated we just have now this new tensor with shape 128. We then move on to the encoder, which is made of several encoder layers. This encoder takes in the sequence from the data set, then we pass it through the embedding layer and add it up. That's we add this embedding output, which is giving us encoding input. We add this up with our positional embeddings, which we just defined. Then from there we simply repeat the encoding layers for number of layers, number of times. So basically that's just a for loop which takes this. We've defined this encoder layers such that we have this list of encoder layers for the number of layers range, and then for every I we just call in the encoder layers, so that once we get out of the loop we have this output. Then we test this encoder layer right here, run that, and that's just fine. We could always have this output it, find that everything works. Our next layer will be the decoder layer. right here. We shall just re-implement what we had in the paper. We start with a multi-attention bottom. So we have two multi-attention actually. We have this first one at the bottom, and then we have this one in the middle before having the feed forward block at the top. For this first multi-attention, we have the inputs, that's this, which comes from the addition of the positional encodings with the actual embeddings. Now notice that here the look ahead masking is set to true, and this is because this multi-head attention layer right here is masked as compared to this other multi-head attention layers, which are unmasked or which do not take into consideration the causal or look ahead masking. Then after getting the output, we have the input plus the output to get this output right here. Then we have the normalization, that's the layer normalization, which now gives a new output, which happens to be the input for this middle multi-attention or multi-head attention layer. Now this middle multi-head attention layer has this look ahead masking set to false. And with this again, we have this Westnut-like addition, we have the normalization, we have the feed forwards input, we pass through our feed forward layer again, the dance 1, the dance 2, the dropout. Notice again that the dance 1 here has the output number of neurons to be 4 times that of the model size. Then we have this feed forward normalization, which gives us our output right here. So we run this, and then we could test this very easily. And there we go, we have our results as expected. Now one point we forgot to mention right here in the decoder layer was actually that once we get into this middle multi-head attention layer, we're taking the queries from the decoder, that's from the decoder's input, that's from this, while the key and the value is actually from the encoder output. You could recall from this architecture that we get the output from this last encoder and then pass it in each and every decoder layer right here. So this, what we're passing in here is actually the key and the values, and the queries come from the input from the data set, which comes from the shifted output actually right here. Looking back at the paper, we could see how we have this query which is passed here, and then we have the keys and the values which come from this last encoder layer into the decoder layers. Before continuing with the decoder layer, we should correct this error right here. Now actually the problem we have with this is that every time we have once we get this encoder input into this and we have this output, normally this output should be used as the new encoder input for the next layer, but this wasn't done right here. So we need to add this, so we need to modify this such that we have the encoder input which is equals the output, such that if we pass this the first time, the second time this encoder input now is taking the value of this output, and so on and so forth right up to the last layer. So we run this again, that's fine, and now we could move forward to the decoder itself. For the decoder right here, it's kind of similar to what we've seen already with the encoder, with just a difference that we have this dense layer, which is this linear layer which was added right here. So that's fine. Now we could run this again and test the decoder. Now the decoder is tested, we can now go straight to the transformer model. Now the transformer model actually is made of the encoder and the decoder, so it's just this model which is like some sort of summary of all what we've seen so far. We define the encoder and the decoder just like the way we've done previously, just like this. So we specify all its input parameters. For the encoder, we have the vocab input size, model size, number of heads, number of layers, and similarly for the decoder. The encoder takes in the inputs while the decoder takes in the pre-outputs. The pre-outputs are the shifted outputs. So we have this sort of input here which gets into the decoder, and also we take the outputs from the encoder and pass it into the decoder. So after this, we have now the decoder outputs. We could now test this transformer and then run it. There we go, we have this model summary. Note that the transformer will just simply, like from here, we simply put in all these parameters. That's clear. We have the two inputs and then the single output right here, which is basically a decoder output. So that has been run already. Now we could go into training and optimization. After compiling the model, we can now start the training. Training goes on for over 1,000 epochs, and yeah, the kind of results we get. So we lay from this loss of about 7.1, the loss drops right up to this value 0.19. So we could continue with training to have smaller loss values. We could also look at the blue score. We now define the translate function, which we'll use to implement the teacher forcing. Firstly, we have the input sentence right here. We convert this into tensor slices. Then we map this using our vectorized input layer we had defined previously. Now the aim of this is actually to be able to convert whatever sentence we have into the vocabulary we had defined already, so that it matches up with the same vocabulary we use in training a model. Then from this, we get this converted input, which we could print out as in one. We could comment this other parts. So we have this commanded, return a known value right here, and then we run this and then call the translate function. So suppose we want to translate a word. We want to translate the word we won. Run that. You see, there we go. So this actually converts this we in its corresponding value in the vocabulary, which is 9, and then 1 corresponding value 49. Let's pick a word which is in the dictionary. Let's say calculator. Run that. You see that we have this value 1, since 0 is for the padding, 1 is for the unknowns, and then 2 is for the start token. So there we go. Let's take this off now. That's fine. So once we have this input, we now go ahead to create the output or the pre-output. We call that, if we have this kind of input, the pre-output actually looks like this, while the output is this. Now we pass in this input, for example, then we have the pre-output, which is initially made of just the start token and then patterns. So we have the start token, which is 2 0 0 0 0 0. So that's what we're going to start with. We pass this, we get the first value. This first value is going to be used in this now. So if we have this G, suppose this G is, for example, 20. So if we have the start token, that's a pre-output, which is this. So suppose we have this kind of pre-output, then after the first step, we're going to have instead 2 20 0 0 0. So that's it. Now once we pass this again, we're going to have another output. Suppose now we have, so initially we had this. If we have another output, suppose now this M, and that the M is, say, takes a value 50, we could have this. So this is modified, we now have 50. We pass it again. Suppose we have this output L, whose value is 45. You see that we're going to have this. Instead of that, we now have 45, and so on and so forth. Now in the example we've chosen, we're actually working with a few number of training examples. That's why our sequence length is restricted to just 5, so that we could test our model quickly. Nonetheless, we could increase this number depending on the number of training examples we have and the kind of training examples or the length of the sentences we have in our training examples. So that said, coming back to this, that's why we define this input 2 as this. So we could now uncomment the section. We define this input 2 as this because initially the start token takes in the value 2 in this vocabulary. We define the final output, and then we define the sequence length. So for I in the range sequence length, basically what we're doing is that we're looping through using the teacher forcing technique, where we start with the first. We're supposed we are starting this first start token 2 0 0 0 0. We pass the value, we get the next. So we're just going step by step. So that's why we have this for I in range sequence length. Now the present input 2 is going to be made of a padding of input 2, and then the rest is going to be made of zeros. Now the zeros will depend on the actual position of I. We could uncomment this. the zeros will depend on the actual position of I. So let's run this. For example, let's say pre input 2. Run that. Now let's take this off. Actually, we have this. Run this now, and there we go. You see that right here, our p input 2 has been printed out. Let's take off this other one right here. Run that, and that's fine. So this is the first input 2. This is what gets in. We have our input 2. We're gonna pad it. The way we pad this is such that when I is 0, we have a value of sequence length -1. So we padding from this, or let's just explain the padding. So suppose we have this tf.pad of a certain value. We have chosen 2. Then we could have, say, we pad from 0 to say 5. Run this. You see that we have the 2. Then we have 5 zeros attached to that. Now if we have this, since our sequence length is 5, actually we need to do sequence length -1 since we have already occupied the first space. So if we run this now, you see there we go. So this is actually what gets in as our input right here. So after going through the pattern for the first time when I is equals 0, this is what we have, and this is what we see right here. Now once we have that, we join it with the input. So we have this input 1, which we've seen already. We have our input 1, then we have our p in 2, which is our pre-output, our shifted output. Then we have the model of predict, because basically our model takes in this input and then the shifted output. So initially our shifted output is this. So because we don't notice other values, we shall notice other values with time. So initially we have just this. We pass that. We have this expand dim so that it could match with the kind of tensors our model takes in, simply because our model considers that we have a batch size dimension. So even if you have to pass one value, you have to add that dimension. So that's basically what we're doing right here. We have this model that predict, we get the values, then we get the maximum or the position of the maximum value, which gives us the output. And the reason we do this is because our model that predict will output a 1-hot vector. So we need to get the exact position and consider that as the output. Now, if this output is equal to 0, then we're going to break out of this loop. Reason being that we are already done. So if we, for example, are having this word we1, you see that when we pass in the word we, for example, we get the output 8. We get an output 8. So let's take this off for now. Take this off and then print out the output. Run this. You see we have this output right here. Okay, we have the output instead 7. So we have this output 7, and then we have this, and then the next output is this. You see that once we get to this point, we actually get out of the loop because we are already done with the translation. So once our model starts outputting a 0, it means we are started to do padding. So we could just get out of this translation loop or this teacher forcing loop. Now, once we have this kind of output 7, what we do is we add +1. The reason why we add +1 is because note that we have 3 different vocabularies. We have the input vocabulary, we have the input vocabulary, we have the pre-output vocabulary, and then we have the output vocabulary. If you could recall with the input vocabulary, let's just take this from here, from what we printed right here. With the input vocabulary, we have this vocabulary size as we have 639 distinct words. For the pre-output, we have 1414. For the output, that's for the pre-output, we have this. For the output, we have 1413. Now notice that there's a difference of just 1 between the two, and this difference comes from the fact that the pre-output has a start token, which this doesn't have. So that start token word is added to this. So it means that if you want to match a word in the output vocabulary with that in the pre-vocabulary, we need to do a modification such that if our output is, for example, like we saw in the example, if we have a 7 here, then in the pre-output this should be an 8 because the second position has already been occupied by the start token. So there's a shift by 1 again right here. So let's come back to this and we'll see why we have this. Then we just simply attach this to our final output. So we get the output, the numpy which is this output we got right here. We simply attach that, and then for the input 2, that's for our new input, we've taken this +1 such that it matches with the vocabulary of the pre-output. So now we have a modified input 2, and that's why you see for the first time, let's print out again the input 2. So let's print out this padded input 2. We have that. We'll come right here, and there we go. So we see that we have this entering our model for the first time, for the second time, and then the next time we have an output of 0. So that's why we get out of this loop. Now we could now see that once we have our final outputs, what's left for us to do is just to loop through this output and then match the given output figures with your respective words. So doing this matching, we just have to do the get vocabulary and I. So for I in the final output. So right here we could print out the final output, take this off, run that again. That's fine. So there we go. So this is actually what we get, and if we match this, it goes to the words nous gagnons. We could test all the words in our database. In our data set, we have words like ask him, see, demande lui, and that works just fine. Recall, to be able to compare two different models, we could always take this into consideration. You could use the blue score and then increase now the number of training examples, train for a longer period of time, while modifying the different hyperparameters so that you could be able to come up with a very robust machine translation system. And also, you may not likely want to translate from French to English or from English to French. You may have a different language you want to translate, maybe your local language. You could feel free to actually create that kind of data set or use already existing data set, and then make use of TensorFlow's tf.data module to train your models very easily, and then come up with a great system which actually works.